The broadcast is now starting. All attendees are in listen-only mode.
Hey everybody, my name is Christopher Callis, and I'm head of cloud security over here at Tavora, and accompanying me is Eddie. Eddie, if you want to
Hey
give yourself an
everyone,
intro.
this is Edward Workparita. I'm a cloud security associate here at Tavora. Nice to virtually meet you all.
Awesome. Thanks, Eddie. So today I wanted to talk to everybody about something that's near and dear to my heart, and that is testing for resiliency in the modern cloud workload. So, improving security and resiliency is a challenge for organizations. We found that most solutions require the introduction of added complexity to a workload's architecture, which in turn does not lead to significant improvements in resiliency. One way to improve resiliency that we have found without the deployment of new complexities is to do something like deploy the workloads to a service mesh. And a great way to test this approach is through resilience testing. So before we start to get into how actually testing resiliency works, let's take a look at the technology that enables our workloads. You see, it's not that one architecture is better than the other. It's deeper than that. Today's workloads span multiple specialized fields that have to address various regulations, and this means that you have various kinds of individuals that specialize in their particular area of operations. Networking, systems, security, application front end stuff, back end stuff, storage stuff. You get the point. In order to understand how to manage this complexity we have to deal with today, I need to take you on a brief look at how operations has evolved over the years. So in the beginning, organizations had one data center with a single server that famously took up that entire room. They called it a mainframe. And this required teams of people to manage, and a lot of this management was at a physical layer. Vacuum tubes, tapes, lots of mechanical parts, lots of things to fail meant there was lots of maintenance to be had. The next step that the industry took was the transition from mainframes to servers. You go from a room-sized calculator to a single rack. It's sexy, sleek, still relatively easy to manage, and most large organizations would have many of these. They were much easier to maintain, and each server generally served a single function, especially with their compliance workloads. But the world got bigger, a global connected economy emerged, and the need to have interconnected systems across the globe became a thing. We had to start to tackle regulations and serve different content based on the country it was being served to. We are now at the rise of the colo data center, both for disaster recovery and for the ability to drive traffic as close to the edge as possible. This complexity evolved, and it started to become very clear that it would soon become impossible to manage by hand. Engineers had to fly to a location to manage these servers, or you had to synchronize teams across various time zones. Additionally, if you took a look at the resources being used on these systems, you maybe see a 10 to 20% CPU usage, 5% memory capacity really being used. So it wasn't necessarily efficient. Then came the hypervisor. Instead of a single application on a single server, you're able to virtualize the operating system. And there was an isolation layer that did not really exist up until this point. So now you can isolate multiple systems on the same machine and take advantage of the additional resources that were previously untouched. And this led to a dramatic increase of systems. We went from thousands to tens of thousands overnight. Now you're running these systems on shared hardware, and there's tremendous reliance on isolation of the OS layer. And this required a huge team of people. Automation went from being a nice future thing to being a requirement. To add to the complexity of this new world, the cloud became a thing. Configuration management tools such as Chef, Puppet, Ansible, Salt were developed, so the administrators only needed to specify the intended end states. Infrastructure as code, tools such as Terraform and CloudFormation allow organizations to manage the complexity of modern infrastructure, and this allowed engineers to use declarative code that allowed consistent enforcement across all systems and networks. And we live in a world where tooling is no longer an optional thing, and there needs to be a strategy to enforce consistency across these complex environments. And time again, the strategy that we see organizations take is to codify their environments. And when I say this, I'm talking about capturing that routine, process, or configuration in a form that allows it to be repeatable, and scalable. Now, there are a couple of ways to accomplish this at a high level. Code can be declarative or it can be imperative. Think of imperative code as your traditional procedural object-level programming languages. In these methods, the imperative code is given a step-by-step process on how to accomplish its end state. Now, with declarative code, we're just specifying the desired end state and letting our tooling decide the best way to achieve it. I really love this. Coming from like a compliance audit backend, diving into systems, looking at things step by step. The old imperative way was way more complex and way more time consuming. With the declarative method, we could validate that these configurations have been applied and they are in their correct end states with just a couple of commands across an entire fleet. So I love this. It's easier to digest and validate for security and compliance teams alike. It means you are no longer locked into a single platform, and the developers have the capability to spread resources across various kinds of infrastructure using similar tooling and maybe just updating a variable or so. So now that we have all of this out of the way, I have everyone on the stream on board with 100% commitment to adopting declarative codification of your workloads. Where do you start? Let's start with what we call configuration management tools. Regardless of how the tool you decide to go with, configuration management is great for ensuring your fleet of systems has the appropriate end state running. These are tools such as Salt, Chef, Puppet, Ansible, and each has their own corresponding Salt state, Chef recipe, Puppet module, and Ansible playbook. In these modules, you specify the condition of the system or fleet, and depending on the mode you have these tools running, they will apply the state throughout the environment. So now that we talked about some configuration management tools, great, your systems are hardened. Work here is done. Like we discussed, environments are way more than just a single system. What do we do to manage the complexity of the rest of our workload? How about the infrastructure side of the house? Tools like Terraform and CloudFormation can be leveraged to manage the complexity of infrastructure at scale. Landing zones are becoming commonplace across all cloud service providers, and these environments are starting to be used similar to containers. Spin up a new account that is identical to a production VPC, test and dispose of it when no longer needed. Some of this is for the core of resiliency is, hey, can we fail multiple AZs and regions just by updating the code? So we have found the greatest way to ensure segmentation isn't in the cloud is at the account level. And these tools are vital at ensuring that no nuances exist between the environments. And this will be key to being successful with future compliance initiatives when we are validating as code, since the environment keeps people away from production and keeps people away from data. We have various CI/CD tools like Jenkins, GitLab CI, Circle CI, Concourse. These tools ensure that there is continuous integration on code that has gone through the appropriate change process. These are amazing tools that allow organizations to enforce their own opinions on environments at a code level and are key to version control workload that we all desire. Next, let's talk about containers. Docker to be specific. We could talk about the different ways to orchestrate it in a future chat, but I really love containers. They are great because they are immutable. This means that they are stateless, just a number that is used when it is needed and disposed of when the time is right. Gone are the days of naming systems, manually configuring them after your favorite significant other, pet, car, or city. The configuration files are declarative, and the containers themselves are immutable. This means if there is a vulnerability in a dependency of a container, Docker's enterprise vulnerability management system, for example, will notify you. And just like with code, you change it from vulnerable to a non-vulnerable version, send out a pull request, and the environment's been updated. Even better yet, leverage a continuous integration tool. Once the change is committed, it will be automatically deployed. No more logging into each system, having SSH exposed and typing apt-get dist upgrade anymore on those tens of thousands of systems within your fleets. Now that we have gone through the infrastructure tools and containers, let's go further in the depth of how resiliency works with your servers. When you think resiliency, think elastic, think immutable.
All right, so let's use a simple tech analogy, pet versus cattle. Aren't they cute? Two dogs are always better than one, am I right? So double the cuteness. So here we have our pets named Lilo and Stitch, who love to play with you out in the backyard and cuddle with you at night. You love them dearly, and life is meaningless when you're apart. But more importantly for this analogy, Lilo and Stitch are pets. So let me go ahead and clarify. First off, they have names, Lilo and Stitch. That name means something and makes them special, different from any other, non-Lilo and Stitches. Second, think about what happens if Lilo got really sick one day. She stops letting you cuddle with her. You had to make the decision to put her down. Now, I know what you're thinking. Lilo and Stitch are fine because this is completely hypothetical, so don't worry. But the point that I'm making is that you would care if something happens to them or if they were ever replaced, right? You probably get it by now where I'm going with this pet and cattle analogy and understand the concept challenges we're trying to achieve over here. So for the purpose of this discussion, let's assume you see the cattle as a polar opposite of Lilo and Stitch. You see the cattle as an interchangeable milk factory of no individual significance whatsoever, and you see these cute puppies as your unique pets rather than a herd of numbered cattle. You want our servers to be interchangeable cattle that is easy to build up, tear down, or to upgrade. You want to be confident that at any time you can rebuild the server exactly how it is now, with minimal effort, minimal downtime, and no impactful difference between old and new, and all without reading any tickets to do it or questioning ourselves if we got it right the first time after the fact. The technical takeaway here is that we want to get ourselves out of the business of treating all of our servers like our pets and more into the mindset of treating the vast majority of these servers like cattle, where they're provisioned using automated process and failure tolerant by design and ready to be traded in and out at any time. So let me go ahead and give you an example. So instead of Lilo running the workload, Cal Server 10 over here is running the workload. And if Cal Server 10 goes down, then Cal Server 11 takes its place to handle the workload. You don't necessarily mind which particular server is doing the work as long as it's getting done. So one goes down, gets pulled out, you press the button, and there, a new one spins up, and on we go. That's how cattle works, and that's the dream. Now that we got the cute puppies and cows out of the way, let's see mutable and immutable in action side by side. So first, here we already finished provisioning our line of version 1 server machines on the mutable and immutable infrastructure. But wait, let me throw you something. Version 2 upgrade is available now, so let's go ahead and upgrade it. So go ahead and look at your left screen here, looking at mutable, for instance, on the left side. To modify these servers to version 2, give it a little wave of the mouse and voila. We successfully applied changes to the same server we have for Stitch and his family. Nice. It lived to see another day. Although applying mutable method works, it's not always peachy. It does come with its own set of problems. And I'll give you an example. For any reason, if for some reason updates don't apply properly, it can increase risk complexity in the production workloads. And it may take hours or even days to debugging this unexpected state of Stitch's servers. Changes to the servers are not necessarily documented either, making the version tracking more difficult. And just to add on to this, technical issues are hard to diagnose or reproduce because servers has a unique configuration or configuration drift that can get lost in translation. But as of right now, looking at this, we're just glad that our pets are still alive and kicking. Now that we're familiar with the mutable infrastructure, let's take a look at what's brewing at the server ranch from the immutable perspective. So go ahead and draw your attention on the right of the screen here. We start off the same process with Stitch's cousin running on V1. But instead of applying changes on the same server as we did with mutable, we're going to enter our cheat code through Terraform. After we finish entering our infrastructure as code, we are now ready to provision and spin up a set of new servers instead of using the old one. And there you have it. You successfully provisioned fresh version 2 servers. Now we can either go ahead and destroy the previous one up on top, or just safekeep it for testing or rollbacks. One of the many benefits of provisioning sets of version 2 servers is that it eliminates configuration drifts, which we'll go ahead and get into in the next part of our code advantages. So I'll go ahead and let you take care of it from here, Chris.
Gracias, Eddie. So now that we have an understanding of the tools that exist and understand that mass codification is clearly the way to manage complexity within our workloads, let's dig into why there is a tendency of organizations to embrace code when things get complex. One of the advantages is static analysis, alerting, and linting. Once code is captured, linting allows an organization to enforce their own opinion on that code. This is commonly done in the form of static analysis and alerting. The OWASP top 10 scans, those type of things. In this, organizations go as little or as complex as they feel necessary. That analysis of code leads to linting, which allows organizations to enforce consistency as the workload matures over time. Think of preventing configuration drift, which would cause issues with compliance. This, again, we have found to be a key component for adoption. Speaking of static analysis and compliance validation, we could start deploying preventative controls. We start taking a look at things like layering in open policy agents. We could do things like Terraform Sentinel policy, where compliance teams can now enforce their opinions on the code and be able to evaluate the environment as code while removing access to production. And this will allow people to keep people away from production, keep people away from data, and really catch those manual iterations that potentially can happen within production. Another advantage is collaboration. This is a huge benefit. Once code has been captured and all teams are really speaking the same language in a common format, we can then iterate with CI/CD tools that we talked about earlier. And this will allow for the automatic building of a workflow that works for collaboration. And this code collaboration we find to be a huge driving force for adoption across teams. And so with the increased complexity in our environments, it's difficult for a single person to reason about an actual workload. Collaboration provides checks and balances, keeps teams on the same page, and version-controlled infrastructure drastically helps manage security and compliance requirements. It also allows for segmentation of duties, which, as many of you know, is a core requirement for some of these compliance standards, such as PCI DSS. So these tools have a lot of modular options, salt states and pillars, chef recipes. There is an intrinsic layer of isolation that allows teams to define their problem within their respected domain, very specifically. And the world does not need to be solved, just really our tiny corner of it. And I joke about this with clients all the time. Treat the workloads like Legos, picking that right yellow Lego with 8 dots to fit the particular workload requirements. So once all the code is captured, one of my favorite things to do is to be able to model the output. This allows us to take these abstract concepts like infrastructure and networking and input them into something that allows us to interrogate our design. For example, with Terraform, it allows you to output your build into a dot file. And you could take this open source format and leverage academic tools to 3D visualize the world that was just built. From here, this is really where we could start with our resilience testing. We would start with a hypothesis and follow up by attempting to disprove that hypothesis. For example, in this scenario, we would do something simple like availability zones need to be fault tolerant. The more challenging it is to prove the hypothesis, the more confident we have found teams will have in their application's ability to handle various errors. And since we have spent significant time discussing the importance of provisioning our workloads as code, we could do something simple like updating our AutoVar file or updating the ELB to not route traffic to a particular zone. So now that we have gone through ways to build modern, immutable workloads, we can start the execution of specific tests or series of tests to validate our workload's ability to handle failure scenarios in production. And we found that intentionally breaking our workloads may sound counterintuitive, but conducting experiments to identify weaknesses in workloads and their underlying systems is crucial for improving resiliency. And thank you for joining our Testing Cloud Resiliency webinar. I'll leave a moment here for any questions on the chat side of the house. Otherwise, definitely feel free to contact us at the links that'll be provided in the webinar invite. Yeah, one of the questions that came through is, should we be testing in production or non-production environments? When you have things codified within the environment, and you have parity between the two, when we're coming through and we're doing our testing, especially early on with some clients, definitely like to do it in a non-prod environment just to see if there is any like low-hanging fruit or some, we don't want to bring down production, but really we find that teams start getting into, really having that confidence build up in their workload once they are actually able to test production and they do have that confidence that the workload is, fault tolerant for whatever hypothesis is actually getting tested. We see common things like this with organizations like Netflix, where they have a tool called Chaos Monkey. And literally what that tool does is go down and take down services to ensure that, their workload is resilient and, they're able to still deliver content even though zones have gone down. Good question. Why the mesh network? Well, because the mesh network really takes it a step back. When you are leveraging a mesh network, you no longer have to do that manual configuration of the environment. For example, in the photo that we have here, imagine a set of EC2s that, A and B are, the front and the back zone are data center 1, data center 2, and then you have service A and service B. And say in data center 2, you can't see my mouse, but these rear sections, say that the B systems go down. Within a service mesh, what would happen is the A systems would then communicate to the separate data center in order to find the B actual services. So service meshes really allow for a lot of flexibility on the networking side and a lot of fault tolerance. And that's why we like to use things like console for the workloads that we help our clients build out. Good questions. All right. Definitely feel free to message us on the side. Again, my name is Chris Callis and joined by my colleague, Eddie. Eddie, thanks again. Really appreciate it. And thank you for attending. Have a good day.
Pleasure. Have a good one, everyone.